The purpose of this lab is to observe the behavior of an object oscillating vertically on a spring. To do so, I made use of physics concepts such as the energy principle and forces to aid my observations. The energy principle follows the formula: change in energy is equal to work from the surroundings plus Q. Formulas for different types of energy exist and are used in this lab, including kinetic energy, 1/2 mass times velocity squared; gravitational potential energy, mass times gravity times the position y; and spring potential energy, 1/2 times k times s squared. For the first part of the experiment, I looked at a recorded video of a mass attached to a spring released from rest. For the second part of the experiment, I used data collected from part 1 to code a model of the system. The result of the lab shows how the energy principle holds true. In part 1, I observed video of a mass oscillating vertically and horizontally on a spring. For the initial conditions, the mass weighed 0.4 kilograms, the spring was stretched with its fixed point above and to the right of the mass, and the mass began at rest. The forces acting on the mass are the gravitational force and the spring force. Using the application tracker, I observed the position data throughout the video and observed how the mass oscillated up and down and left and right. In part 2, I used the position data from tracker and a simulated model to make more observations. In the code, I assigned initial conditions including the initial system energies. To calculate the kinetic energy, I used the object's mass and its current velocity. To calculate the gravitational potential energy, I used the object's mass, the gravitation constant near the Earth's surface, and the object's current y position. To calculate the spring's potential energy, I used the spring constant, which I found using the period oscillation formula, and I used the spring's displacement from its equilibrium. Due to how the spring in this model is the object, the spring, and the Earth, there are no surroundings doing work on the system. Therefore, the total energy is 0. Following the model's initial conditions, I then used the code that would update the model for every time step. I calculated the net force on the object by using the gravitational force formula and the spring force formula. Then I used Newton's second law to update the object's velocity and the position update formula to simulate the object's motion. I also updated the motion of the spring throughout the simulation using the position of the fixed end of the spring and the position of the object it was attached to. I then used the same energy formulas from before to update the different energies of the system. By running the code, it displays the motion of an object attached to a spring. It oscillates up and down as well as left and right. The code also presents a graph that displays the values for different types of energy throughout the simulation. These values, like the motion of the object, oscillate as well. By inserting the position data from tracker into the simulation, it creates two position over time graphs for both the x component and y components of the objects. The graphs compare the real-world model and the computed model of the system. The x position over time data for the real-world model appears to be a slightly translated version of the computed data. The y position over time data for the real-world model appears to be a less amplified version of the computed data. In the lab, there were possible cases for error. First, the calculations assume that the spring has no mass. Another example is that the time between data points could have been measured imperfectly. In the model, the energy principle is satisfied. Throughout the simulation, each type of energy changes values, but the sum of them always remains to be 0, which is the total energy of the system. By analyzing the data I collected using tracker, I found that the oscillation period of the mass is 8/5 seconds for the x position and 3/2 seconds for the y position. This shows that the mass is oscillating a little faster for the y position. Their differences are likely due to the different forces acting on the mass, such as the gravitational force and the spring force. In conclusion, formulas of forces and energies can be used to describe systems such as the one used in this lab.